So now we're going to look at the op amp as a non-inverting comparator. The op amp I'm going to be using is the LM358. I got it out of this kit and it has the pin layout on there. I also got it drawn on the diagram that I drew. And it shares a spot with the NE555 right there. So when you pull it out, I mean, you should do this anyways, but you got to look at the part number. Make sure you have the right integrated circuit. So pretty sure the divot goes to the left like that. And you can see this with the bare eye. I think it's kind of worn down a little bit over time. And let's move the light there. But yeah, there it is, LM358. I know it doesn't show up very good. And then there's P, so it should be an improved version from the original if I remember right. So a lot of integrated circuits were originally made a long time ago, and then they got better at making them better, and so they are updated from the original. That lets you know that. So all the new ones probably say P on them. Now, we got that inserted in the board. You have to power the integrated circuit, and I already have a jumper, pin 8 there, positive supply, VCC, commonly referred to, and then pin number 4 to the negative supply, right there, ground. So we got it powered. The main thing to remember with op amps is the output voltage, because the voltage does change, it doesn't just turn on or off, is more like the non-inverting input voltage than the inverting input voltage. Now, the non-inverting is pin number 3, inverting is pin number 2, so they are lined up like you see on the sheet. In fact, I wrote the pin numbers on there. But some schematics may swap the positions right there. That's something important to be aware of. So, let's get to the reference voltage. And so, we're going to just take a couple 10,000 ohm resistors and going to pin 2, the inverting input. That'll give us half of the supply voltage at that point, whatever the supply voltage is. So in this case, it's going to be 2.5 volts out of 5 when I apply power, but whatever the supply voltage is, it'll be half of that. So that's something to be aware of. Other circuits, you may take advantage of the voltage changing at your reference voltage when the supply voltage changes, but not for this one. So there you can see positive and negative. Basic voltage divider stuff. Half the resistance to positive supply, half the resistance to negative supply. Inputs don't let current in or out. Very important to remember. Now, I got this jumper coming over to this spot right there. You can see we got a trim pot. So that's a potentiometer symbol right there. That you can see there's power on both ends of a resistive element and a wiper that slides along them. And ones where you'll be using it all the time, high power and stuff, they're larger. This is the smaller version, trimmer potentiometer. So these are kind of meant to be built into circuits where you'll kind of be setting a setting and then leaving it there for a while. But you can change it a lot too. It's not like these are really delicate. You only got a few changes. But in any case, we're going to slide it in. I usually like to put the grooves in there. But the main thing is whichever the arrow is pointing closer to, the voltage will be closer to that voltage. So right now we'll get 5 volts if power was applied, and if I turn it all the way down, 0 volts with power applied. And just like the resistors, we got half the resistance positive supply, half the resistance to the negative supply. If I put it halfway, then again, half the resistance on each side right there, we'll get around 2.5 volts out. So something to be aware of. This is a single turn trim pot. There's other ones. They're usually like rectangle shape with a little screw thing. You can turn them many times. So as you turn it, it just moves the wiper a little bit along the resistive element. So that you can get a lot more precision. These aren't as precise. So in any case, there we go. That is it for the circuit. It's going to compare those two voltages. The output will be more like the voltage of the non-inverting input. So we're going to add LEDs to illustrate that right there. And so let's work our way over here. For some reason I like to wire that one better. So you can see with positive supply, we're going to put a 1000 ohm resistor and an LED with them. One thing to be aware of, whenever you're looking at schematics, you don't have to necessarily put it in the order that you see on there. So I want to put the blue LED, just so I can keep these two pins together. I try to do that as much as possible so I don't have to bend them out of the way. Long lead, the anode, has to be towards the positive supply. As you can see there, that's the anode. That's the short lead, the cathode, right there, headed to the output. So even though I'm going directly to the positive supply instead of the output, the long lead, the anode, has to be going there. And then I'll take a 1000 ohm resistor. Blue LEDs are brighter than red LEDs. And I thought these op amps connect to ground pretty well. But if you saw the last video with the load, it really did not do as well as I thought. Connected to the positive supply better. So I'm also aiming through the camera. So I was off a little bit. But there we go. Doesn't matter which direction you put the resistors in though. Does for LEDs and other diodes. The resistor, you can put it in either direction. But usually you want to line it up so you can read the color code, which I know is not showing up as good on camera as it would in person. Now we can we can turn the light. That'll help a little bit. So when the output is high, I like to use a red LED to indicate that. Red for high, blue for low for the output. That's just how I color code it. That's not a a rule that you have to follow or something. And I didn't really give a good spot for the negative supply. I'll add that jumper now. So now I was going to just tack in the jumper like I did with those, but since this video is kind of for those that are not used to building on breadboards, I will take the time to add this one jumper right there. So there we go. We got a spot directly to negative supply. And what we just did goes with pretty much all these jumpers, is that we took the negative supply right there, and now we made this whole row part of the negative supply. Just that those 3 extra dots right there. So that's what jumpers basically do. They take whatever row you got and make another row part of that row electrically. Now we have the LED. So the short lead, the cathode, needs to head towards the negative supply. Long lead, the anode, towards the output. But I'm going to swap the resistor and LED position again, just because I like how that looks. Otherwise, I could put the LED upside down, or turn it around, I mean, at the output, kind of like I did with the blue LED, turning it around. Usually I like to put the anode above the cathode, but sometimes I'll make exceptions. And then 220 ohm resistor. So you notice we have a much lower value resistor, about 1/4 of the value for the red LED than the blue LED. We'll actually get a lot more current through the red LED, but we kind of need to, because blue LEDs are just naturally brighter. You put the same current through the two of them, and they're going to be a lot brighter. So blue LED is going to be pretty bright at 3 milliamps of current. Red LED not so bright at 3 milliamps of current. So I'm generally trying to get between like 10 and 15 milliamps of current for the red LED versus the blue. And then also, the op amp really isn't meant for providing power. These LEDs will throw off the output voltage a bit. It never connects fully to the positive supply. Usually you lose about 1.5 volts, 2 volts with a light load. And the output connects to ground really well with no load. And I learned in the last video, not so good with a load. So just something to be aware of. But this is a demonstration circuit just to get you familiar with the non-inverting comparator. So now we're going to power this, and you have a lot of options when it comes to powering stuff. Best is just when you're learning is to just have a bench power supply. This is a portable version right there, where you can set a voltage and a maximum current. That's the maximum current for an LED right there. They're kind of the most delicate component, and so there's no way we can put too much current through this circuit, other than brief spikes. Sometimes it takes a little bit for it to only provide 20 milliamps of current. But yeah, I got these header pins right there. The longer end is plugged into the board, and actually with this red one, I'm going to go to the middle one. That will make things more stable, especially with this cheap board right there. The connections are kind of loose. And so, in any case, let's try not to drag this out too long. And there we go. So, probably be better to turn the power supply off before you connect the alligator clips. But that's okay. If you have a battery or something where there is no on-off, then you definitely want to detach the jumpers while you're building the circuit. But with the power supply like this, you can just press the power button, turn it off right there while you're building. So that's what I've been doing recently, but not really showing all this detail. So I'm going to show a little bit extra more because I intend this for absolute beginners, basically. So you can see we got the blue LED lit up. That tells me the output is connected to ground as good as it can. And therefore, we got that current path right there. And in a perfect world, we would have about 3 volts across the 1000 ohm resistor because the red LED drops a couple volts if it was a direct connection to ground. And we would have 3 milliamps of current. And I think we're falling a bit short of that. Semiconductors conduct a little bit better as they warm up, so I think that's why we went from 1 milliamp to 2 milliamps. But this isn't as accurate as a multimeter. Be aware of that. Never look at, especially this power supply, as being precise right there with how much current it is providing. So, in any case, blue LED lit up. Tells me the trim pot is low enough. I'll go even lower, but we're less than half of the supply voltage. This should be pretty much spot on half. This isn't going to be exact 5 volts making it to the thing. It's going to be to the circuit. It's going to be slightly less anyways. Another thing to be aware of. These are not precise voltages, but should be close enough. Now, we went above about 2.5 volts approximately. Now you can see the red LED lit up. And that's because we set a reference voltage. That's the main thing. So we got our changing voltage. This could be coming from light dependent resistor and a fixed resistor as a voltage divider, where the voltage changes as light changes. So I've done a lot of circuits like that. Look for those if that sounds interesting. But instead we're using the trim pot just to change it, because when you're learning about the circuit, you should manually change the signal voltage so you have a real good feel for what it's doing. And then once you got that established, you can see the LEDs. That's telling me the trim pot is lower than halfway, closer to ground, right there, negative supply. Red LED, now it's closer to the positive supply right there, because I know that voltage right there. So a lot of circuits can't really tell you what they're doing, but if they have a load that does something, a lot of times you can tell from the load what the circuit is doing. So, in any case, I'm going to end it there. Again, really long because it was made for absolute beginners. I have shorter versions of these videos that I did before, but for now I'm going to focus on absolute beginners. So I'm going to go slow and explain things in a lot of detail. I didn't mention this yet. I use 10,000 ohm resistors. That's just commonly used. Doesn't matter what exact values you use, as long as they're equal values right there. But we don't want to waste current. So 10K is commonly used. It'll definitely be strong enough. There'll be enough current flowing through here to give you a strong voltage as far as these inputs. These inputs don't let current in or out. They just look at the voltage there. But you have to get current flowing through the resistors in order to build up that voltage, to get a division of the voltage. So you could go higher. It'll work just fine. But 10K is just commonly used. Same with the trim pots there. 10K is the most commonly used trim pot for whatever reason. So that's probably what you got. They commonly come in kits and stuff. So I'm using 10K right there. I don't have to. Any other value trim pot will work. What matters the most is that the position of the trim pot wiper right there. So these are not critical. You can substitute them. Just make sure they're equal value right there, and you'll do just fine. You could also use unequal values to get a different voltage and experiment with that. That's part of the learning process. You don't have to build circuits exactly as you see them. Try to make as many variations as you can, especially if you got one that'll be more useful to you than what you see in the schematic. Schematics are just a starting point for your learning. You're supposed to build on them from there. So in any case, that's it. Thanks for watching. Make sure you check out one of the other videos I posted on the screen, and check out links down below. They all help out a lot. I'll see you in the next video.